Welcome to everybody. Okay, what we want to talk about, let me describe it by a quote I saw from the CEO from BMW, a little bit more than 1 year ago, where he was saying, look, the ones who will be winning the race in automotive won't be the ones with the largest screen in the vehicle or who will write the longest program code. The ones who will be winning, these are the ones who will offer the best emotional experience for drivers. And that's our focus at VI-Grade. We want to help our customers to assess the driving experience throughout the development process and cut development time during this process. So when we talk about driving experience, we need to talk about, or at least we are grouping it in 3 different areas. The first one is, let's say, as you wish, the classical driving experience. So the relationship between the driver and the vehicle. So how does the vehicle react to the driver inputs? And these are usually described by the ride, handling, and NVH characteristics. This area has been, from the beginning of cars a long time ago, always one area defining the driving experience. We now have 2 additional areas which are gaining importance during the recent years. The one area is the interaction between the driver and all the electronic assistants, so advanced driving assistance systems or even autonomous driving. So how is the experience there? Does the driver feel comfortable in the cooperation with these assistants? And the third, maybe related to the previous one, is the interaction with the driver and the controls element on the dashboard, on the steering wheel, and so on. So usually described by human-machine interface. Historically, if you wanted to assess the driving experience, okay, you need to have a car. But this means you need to have prototypes. Prototypes, as we all know, are expensive and they come pretty late in the development process. Again, that's our focus at VI-Grade. We want to provide you simulators and software which help you to assess the driving experience from early development up to detailed design. In order to do this, we offer you 3 product lines: simulation software, our driving simulators, and our hardware-in-the-loop solutions. Before we dive deeper into our offering, I was thinking, why don't I share you a customer story which hopefully illustrates what we are trying to accomplish and how customers of ours are using these tools. The examples I picked is from Mercedes-AMG. You see this car here. This is a special car called the Project One. So it is a street legal car with the Formula One engine. It was a special car which where the development was undertaken by AMG on the occasion of their 50th year of anniversary. If you're interested in this car, I have to disappoint you. I think there was only a limited number of cars produced, and from my knowledge, they all have been sold. But let's have a look on how AMG has been using our technology in the development process of this car.
During a test, we got the measurement data where we can have a look at G's and how the car responds to the driver. The specialty about the Project One cell we see here is we got like torque force feedback, torque machine, the full braking system from pedal to brake pads. Today we got Maro Engel coming round. He won the 24 hours race at the Nürburgring in 2016, so he knows his way exactly around the Nürburgring. With a race driver, you got really reproductive driving, so you can constantly go into the same direction and same spots and analyze changes pretty exactly. They're used to drive these kind of performances, so they give you direct feedback and precise feedback.
Die Beschleunigung ist natürlich schon mega.
Sitting in the car feels amazing. I mean, it's such an amazing project, and when you pull away in the simulator, you feel straight away, you know, the huge power, very high precision. The car is really all about performance, and you can feel that, and it puts a smile on your face.
I think you heard the last sentence from this race driver. He said it puts a smile on your face. And this, to me, when I hear that a professional race driver who likes to drive real cars on real roads also gets a smile on his face while he is experiencing a new design on the simulator. So for the ones who are not so familiar with the simulator technology, so how it works, you have a digital twin of a new car design, and you then, as a driver, provide input to this digital twin. The computer model provides back displacements, accelerations of the vehicle, and this then is replicated in the simulator. And again, what's also important that you get the right impression or immersion of the behavior of the vehicle. It's not only about your vibrations, it's about the sound, and it is about the environment, so that all your three senses are excited and synchronized so that you get the right feeling and the right immersion. Okay, maybe you also have seen it. So in this simulator, this was not a pure simulation model. There was a combination, Michael was addressing this, a combination of, if you wish, here is our digital twin of the vehicle, the powertrain, and the damper model. But then certain elements were not realized in software, they were realized as hardware. So like the powertrain control unit, the suspension control unit, and the dashboard. In addition to this, the brake system also was realized in hardware, so that on the touch points of your brake pedal, you get a very realistic feeling. So in a way, not in a way, this already is a hardware in the loop configuration, where the digital vehicle model is combined with hardware, be it either the brake system or the different controllers. Let's now have a closer look at the hardware offering, or the hardware in the loop offering you can expect from VI-Grade and our sister company, Concurrent Real Time. When we talk about these solutions, we like you to remember three things. Our solutions are high performant. Our solutions guarantee hard real time, which is particularly important for mission critical applications or safety critical applications. And our solutions are offering an open environment. You may say, okay, everybody can claim this. How do you ensure this, or what are the foundations to this? First, the operating system we are basing our solution on is based on Red Hawk Linux, so that you get the hard real time in combination with our real-time software stack, which helps you to easily integrate this into our whole environment of driving simulators and so on. In addition, what we do, we integrate the latest and greatest commercial off-the-shelf components And last but not least, we leverage their more than 50 years expertise, which our colleagues from Concurrent have accumulated over the years. So core to this is the black system you see here. You can have a different configuration, which we call AutoHawk. And we offer this in various configurations. So you can start with 8 core machines and up to 60 core machines. So you get the high performance through multi-core technology and the usage of, for example, here we have different chips from Intel for the 8 core machines to the 60 core machine. And then in addition to this, okay, you need memory, you need disk, you need the interfaces. You also need, if you want, for example, to model high-speed events like sensors or something in electric motors, you also have FPGA boards. And then you have simulation workbench as the glue who is bringing these things together. And this might be better explained in this next slide. So basically, it starts our offering. You have AutoHawk, the hardware, with different I/O cards like I talked about, FPGA, and so on, either EtherCAT, Ethernet, and so on. On the other side, you have the software stack from VI-Grade, which manages the digital twin of the vehicle, of the environment, of the traffic, of the sensors, drivers, and scenarios, and so on. And like I mentioned before, then simulation workbench is the glue which is bringing all these different components together. You have tools for test automation. You connect this with the device under test, and then you test it as either on a standalone test rig or with the simulators or even within a real vehicle. I was thinking, should I now give you 10, 20 slides where I dive into the details of our different offerings? Or wouldn't it be more interesting for you if I just shared some customer case studies with you? And we just had a conference, it's now roughly 1 month ago, which we call the Zero Prototype Summit. This was a gathering in Udine in northern Italy. We had 300 people there, 1,000 people connected virtually. And we had a couple of quite a lot of customer presentations. Let's say when we looked at what was common themes at our Zero Prototype Summit, when we talk about hardware in the loop, I think we could summarize it under the simple word more. So what we have seen is customers wanted to integrate more ECUs. They wanted to connect more hardware components to a simulator. Others were interested in more detailed multi-body models. And there were people who were saying, we need to do more of the advanced controls. And the case studies I'm going to show you will address these kind of things. But before we go to the case studies, I was thinking, let's have a run through or walk through the exhibition we had. So this is, I think, a 3-minute video just of some video captured of the different exhibitions we had at the conference. For example, that's the first thing. Okay, people wanting to integrate more hardware in their digital twin simulation. So here you see a vehicle model, and now instead of using a mathematical model of a damper, now you also have the ability to do to integrate the actual damper behavior in your model. The damper here for show purposes is a scaled down damper, so you need to do some scaling, but I think you're getting the idea. So instead, in the later time of the process, instead of using the mathematical model, you use a digital twin. We're now moving to the ADAS demonstration. So in ADAS, okay, you need to have models for your camera and for your radar sensor. Initially, you do this again with digital versions, where, for example, here, I think it's a lane keeping system, which we test on the simulator. And then in later stages, you want to replace your digital model of camera and radar by real camera and real radar system. And that's what you see here. It's a combination from MegaRide with their camera model and Rode and Schwarz for their radar model. Steering behavior always defines is one of the key DNA of a vehicle. And again, early in the process, you have a digital twin, you have a mathematical model of your steering, and later in your development process, you may want to test the actual steering, and this is what you see here at the booth of M Dynamics. So they not only have actual steering there, but also an actual brake system, so that you replace the digital representation of your steering model and or the braking model by the actual behavior, so that you then, particularly on the touch points on your steering wheel and on the brake pedal, you get a more realistic feeling. Same thing here. Now we use a different simulator. It's a driver in motion simulator where you also have large displacements, but the concept here is the same thing. We have a digital model of the car, of the environment, and initially we use a digital model of the steering. And in this demonstration, we also take then the actual steering, what you see here on the right-hand side. So these were just a little bit so that I give you an impression. These were the things which were shown at the conference and where people could experience these simulators live. What I now want to do is go into the presentations and share some of the presentations with you. And let's start with the first one. I said more ECUs. And this was a presentation from Bugatti Rematch, where they talked about how they coupled and why they coupled multiple ECUs HiL system with their driver-in-the-loop simulator. For all the case studies I'm showing you, I will only show 1 or 2 or 3 slides. If you're interested in the complete presentation, let us know, or just go to YouTube, give in VI Grade ZBS 2024, and you will find all the presentations which were given there, and you could listen to them and also find more details. So Bugatti, first of all, okay, why do they do this? So let's say, you know, this hardware-in-the-loop solutions, they let you focus on your ECUs. They let you do a lot of testing on reliability and function on your ECUs. But let's say if you have a HiL test rig just isolated, okay, you can test the function, but you're missing the driver subjective feedback. Subjective feedback you get on these driver-in-the-loop simulators, You can use them very early when you don't have any ECUs. As soon as you have a model, you can collect driver feedback, but you're missing the physical, the validation of the physical ECUs. And then, okay, so what Bugatti Rimac realized that they now connected their HiL test rig, where they're testing different ECUs with the driver-in-the-loop simulator. So now they can test the system together. They can evaluate, tune, and debug the entire torque system. They could evaluate and tune the drivability performance of the vehicle. And they quickly generate logs to pinpoint issues they detected with software and hardware suppliers. So again, if you're looking for more details, go to YouTube or let us know, and we can send you the link, and you can find there more details. I talked already a bit about the connection of actual steering systems with our driver-in-the-loop simulators. So this was presented and realized by M Dynamics. So not sure how many people know M Dynamics. They're quite well known in the German-speaking market. Originally started by Professor Pfeffer from the University of Munich. And they know a lot when it comes to steering, modeling steering systems, and they're also generating hardware-in-the-loop setups for steering systems, so that you can test the ADAS function. You can use it for steering field development, ECU functional testing, and tire testing. And again, this has been, or we have been working with them so that you can seamlessly integrate it into our line of simulators. Talking about steering systems, there was a presentation from Mercedes-Benz where it was simulator-based virtual prototyping of vehicle steering. Starting point here is BMW, not BMW, sorry to Mercedes. Mercedes has been using this ride simulator for quite some time. So initially, this simulator was used, okay, you take your seat, and then they are playing back measured signals on this simulator. So measured signals was to assess the ride and ride behavior of a future vehicle. What Leonard now is focusing on is expanding this test rig. So first, put a steering wheel on there so that you can drive the vehicle. In order to drive it, you need to have a digital twin of your vehicle. He has chosen to use a detailed multi-body vehicle model modeled in SimPack. You need to have a digital representation of your proving ground, and then you need a powerful hardware, in this case AutoHawk, in order to do the real-time computing. So the challenge here is you're now, instead of working with simplified vehicle models, Leonard is now using a detailed multi-body model. And he could run this detailed multi-body model by taking advantage of AutoHawk, its high performance, and its multi-core capability, so that he can distribute the digital twin of the vehicle to multiple cores, then even can do the tires on other cores. And with this, bringing all this together with Simulation Workbench, he can ensure that he now can drive the digital twin on this test rig and assess that, and then use the test rig to evaluate the future steering behavior or the steering behavior of this new design. This was not the only presentation dealing with detailed multi-body models, where here the motivation for this presentation from Iliada and Mahindra was different. So to optimize the performance of a battery electric vehicle, and the special case here for this battery electric vehicle was the vehicle had a rear twist beam suspension. And for the ones who are working in the field of vehicle dynamics and modeling, you know, a twist beam is a tricky thing. So modeling the twist beam with a reduced order model has its challenges. And so they were thinking, oh, isn't it easier if we use a detailed multi-body model of this vehicle, including the twist beam? So then, for example, when they want to do some parameter studies, modifying some geometry of the twist beam, they wanted to do this on the simulator and not always go back, okay, generate some new input files. And this is why they have chosen in their case, Adam's real time. If you have seen presentations from Iliada before, the nice thing is they come up with metrics. So that they talk about, okay, what did I achieve with offline simulation? How could I mature the design through simulator usage? And what was still left for hardware prototype testing? And here they show a little bit how the performance for kinematics and compliance. So initially the design, they met the design targets only by 80%. Through the use of the simulator, they could get to 92%. And even there, if you are within 2%, they even could higher. And basically they say it for the kinematic properties and for the compliance properties. And, oops. Just give me a second, computer. Okay, so you see here how the design evolved. So the red are the initial design, and then the green. So basically, on the response delay, roll damping, and agility, they came close to the target. So they accomplished everything like this in 6 months. They could look at 25 different hard points, 20 different, more than 20 layouts of the cross beam, 8 cross beam designs, 10 bushing simulations, and they did all of this in through 4 driving simulator sessions, where they tested 20 variants and validated the concept design, and did all of this with the virtual model. So I think quite a nice achievement. So when we talk about multi-body models, the nice thing, if you do a detailed multi-body model, you have your detailed suspension, you can model flexible components, and you can use higher order models. But if we look at the current state, it requires a powerful real-time hardware, and often, even with our hardware, sometimes you need to do some simplification of your detailed multi-body model. This was a motivation for our colleagues at Concurrent Real-Time to also see, okay, what can we do in order to accelerate or speed up our hardware? And Anish, he presented our conference some really new results where they used an off-the-shelf AutoHawk, which had a base clock of roughly 4 gigahertz. and there he used 8 cores. And the target there often is, if you do these kind of simulations, you want to have a 1 millisecond loop time. And there, the model we got there, okay, it took us too long. If we now use some new technology where we overclock our CPUs here up to 5.2 gigahertz, and by using only 6 cores, we could exceed the target. So now 700 microseconds. So basically, then the value there to the customer is you don't have to spend time on simplifying your model. Even more complicated models can be run in real time. But of course, I think we all know this. The faster the hardware gets, you will get innovative and you will model more and more details. So this will be a never-ending story. So I think at the end, you can say vehicle models will take 1 millisecond because you will always use the computer hardware, the performance you have at your hands in order to come up with more details which you could model. Okay, so we're coming to the case, and I talked about this. So we talked about more ECUs, more hardware components, more detailed multi-body models, and now let's talk about more advanced controls. And this presentation was given by Politecnico di Milano. So for the ones who follow autonomous racing, University or Politecnico di Milano should be familiar to you. This university participates in these autonomous racing competitions. And my understanding is there was one multiple times. And their presentation was focused on leveraging VR-grade solutions for autonomous perception and control optimization. So his presentation, so Alberto presented, was on 2 things. Topic 1 was how they were using our simulators in order to generate training data for their perception algorithm. You know, when you do machine learning, you need to have training data, and so they were quite innovative. So they used our world sim, that's our solution for digital twins of the environment. So they used world sim in combination with our driving simulators in order to generate training data for their machine learning algorithms. So this is for the perception piece. You know, always autonomous vehicles, first you need to understand where you are. And once you understood this, then you can decide what to do. So for the first thing, they do machine learning. And the second thing, what to do, this is where they use control optimization. And before we talk about what they did there in detail, let me also share with you some impression from the Mille Miglia. So Mille Miglia is a famous event in Italy. So Mille Miglia, okay, 1,000 miles, where usually mostly historic cars participated there. But the University of Milano took this opportunity to also take their autonomous vehicles, so basically modified Maserati, and also participating in this. Yeah, it's not really a race, but in this event. Like we said, Mille Miglia, 1,000 miles. So roughly, my understanding is they used between 300 to 400 kilometers. The car was driving autonomously. As you see, there's still a driver in the seat just for safety reasons, but it was equipped with the camera things. And like I said, if you're more interested in also the first, the perception part, I would invite you again to go to our YouTube channel and listen to the presentation. I want to talk about the controls part. And here they came up, I'm not sure whether they're the original author of this term, twin in the loop. You know, for the ones who are doing controls development, there is one of the modern control things is MPC, so model predictive controls. And there you have a mathematical model of the system you want to control. And often this mathematical model, okay, has some simplifications. So it's a bunch of equations. What they were thinking here is, why do we need to do simplifications? Can't we use powerful hardware? In this context, it was AutoHawk on board. So basically they put our real-time system next to the driver's seat. And then they were executing throughout these 300 to 400 kilometers simulation of VI-car real-time, our non-linear vehicle dynamics model, and now driven by the actual inputs from the vehicle, from the autonomous algorithm. And they were looking here at the two different approaches, where they're using the twin in the loop as a filtering, as an observer. And then they used it also here as in the control loop. So both cases, idea, instead of using simplified equations, you're using non-linear equations for the controls part of the autonomous vehicle. And these are just some results from them. So basically, they're showing that the twin in the loop, in the control loop, shows a lot better tracking to the desired signal. So just an example about the possibilities you have with a system like AutoHawk. So when you have very powerful compute environment, so that you also can execute non-linear vehicle models in real time. All of this technology, powerful simulators, powerful hardware-in-the-loop systems are nice, gives you the opportunity, but one, at least from my point of view, one important thing is, in order to implement this into your development process, you need to have a process in place where you generate all the digital twins you need during this development, so that they are available in the when you need them at the accuracy you're needing them. And if you're interested in this topic, I really would recommend that you dive into the presentation from Mercedes-AMG, where they were talking about their virtual garage. So basically, there are simulation experts who make these digital twins of all the vehicles which are under development available to everybody in the development organization, so that they can dynamically configure the requested model, which have been validated, and then make these models available to the different consumers, whether these are the driver-in-the-loop people who are sitting on a simulator, whether these are the hardware-in-the-loop people who validate ECUs, people who do software-in-the-loop simulations or model-in-the-loop simulations, particularly the software-in-the-loop people, so where you do constant integration, constant testing in the cloud. And the nice part here is the models which are used on a driving simulator have very high accuracy and are validated, because these professional drivers, they will very quickly realize that there's something isn't right in the model. So I think this is what the colleagues here at Mercedes-AMG appreciate. Okay, when they use hardware-in-the-loop, software-in-the-loop, or model-in-the-loop, they know the digital twin representation of the vehicle model is validated and they can rely on. That's what I wanted to share with you. So hopefully you got one or two insights, what you can achieve when you combine digital twins with simulators, with hardware-in-the-loop. And just to summarize, you can get to higher innovation, like this car, the AMG car we talked about. This car broke a new record on the Nürburgring. You can get to shorter development time, like Volvo. They were 2 times faster, or you can achieve less prototypes, like NIO reported it, where they had 40% prototype reduction. So thank you for listening, and I'm now interested in the questions you might have.